Okay, the last two chapters were called solids and liquids. So if you guessed that this chapter would be called gases, then you're right. I want to talk about the atmosphere, atmospheric pressure and how we measure it, Boyle's law, and buoyancy of air, Bernoulli's principle, and plasma. So we are surrounded by an ocean of air, and this air exerts pressure. And these two little hemispheres are not glued together, but they're just pressed together and all the air has been pumped out. So these two guys are trying to pull them apart, but they can't. And the reason for that is that this ocean of air around us is pressing inwards on either side of this hemisphere and holding it together. So this just shows how much air pressure there is. Air pressure is caused by the weight of the air above us, and it can vary from one place to another on Earth. And in fact, measurements of air pressure can be used to predict weather conditions. So pressure is exerted against bodies that are immersed in the atmosphere, and it results from the weight of the air above us. And it turns out that here on Earth, around us right now, the atmospheric pressure is 101 kilopascals. You learned previously that a pascal is 1 Newton per meter squared. So that means every 1 meter squared of area is being pressed down with 100,000 newtons of force. That's almost the weight of 10,000 kilograms or 10 tons, so it's quite a lot. But I guess since it's around us all the time, we don't even notice it. One consequence of atmospheric pressure is that we can use suction to pump things. So if you pump out a vacuum, then the air pressure can actually push a liquid up a straw or up a big tube. And it turns out that if you have a big column of water being pushed up, then if that column of water is 10.3 meters high, then the pressure at the bottom is the same as atmospheric pressure. And so that's as high as the atmosphere can be used to push water. So above that limit, you have to use some sort of a mechanical pump. A barometer is a device used to measure atmospheric pressure. And what it is the column of mercury, liquid metal in a tube, and above it is a little bit of vacuum or a little bit of mercury vapor. And then it's sitting in a dish which is exposed to the atmosphere. And the height of the mercury column tells us the atmospheric pressure. And atmospheric pressure can actually decrease if you go up. So a barometer can be used as an altimeter to measure your altitude. But the basic principle is that this column of mercury exerts a pressure on the mercury in the dish, and that's equal to the atmospheric pressure. And when they're equal, it turns out that the column of mercury is about 760 millimeters high. Boyle's law says that if you have an enclosed gas at some temperature, the pressure and the volume of the gas are inversely proportional, meaning that if you decrease the volume, you increase the pressure, or if you increase the volume, you'll decrease the pressure. We kind of know this intuitively. If we take a paper bag and we compress it, then the pressure in there will increase, and it might even pop the bag. And it is proportional so that if pressure is doubled, the volume goes down by a factor of 2. So here is Hewitt's way of using font size to kind of give you the idea. PV before equals PV after. So a large pressure would correspond to a small volume. That's, if you change it to a smaller pressure, that would correspond to a larger volume. So we talked about Archimedes' principle back in the liquids chapter, but it applies to air as well as liquids. An object that is surrounded by air is buoyed up by a force that's equal to the weight of the air displaced. That's what's holding up this fish that's filled with helium. So when the weight of the air displaced by an object is greater than the weight of the object, it rises. And that's true for these helium balloons because they're less dense than air. When the weight of the air displaced by an object equals the weight of the whole object, like when it's being held down by these rocks, then it just hovers there in air. And if the weight of the air that's displaced by an object is less than the weight of the object, then it's not supported by the air. That's why you and I are not supported by the air, is that we displace a little bit of air, but we're much more dense than that, so we weigh more than the air we displace. So you can fill a balloon with gas, and that will hold up a balloon, and that can be buoyant if the gas inside has a very low density. So for example, a hydrogen balloon will rise up in the air. But hydrogen is flammable, so we don't usually use that. We use the next best thing, which is helium. That's an inert gas, so it's a little safer. But also, if you just heat the air, it turns out that high temperature air has a lower density than lower temperature air, and so that will also rise. And it will rise up to some point where the atmosphere has become less dense, and so it stops rising after a while because the weight of the air that's displaced is less. Bernoulli's principle, discovered in the 15th century, states that where the speed of a fluid increases, the internal pressure of the fluid decreases, and vice versa, meaning that if the pressure increases, then that corresponds to a fluid speed that's decreasing. And this applies, to a smooth, steady flow. So here is a picture of water streamlines going to the right, and for some reason in this tube the cross-section has decreased, so it gets narrower here. So when these lines get closer together, the flow speed is greater, and this fluid on this side, or gas, is a lower pressure than the fluid on this side. So the wider flow speed is less, and the pressure is greater. And when it's narrower, the flow speed is more, and the pressure is less. Some applications: if you blow on the top of the surface of paper, the paper will rise up, and that's the reason for that is that the pressure of the moving air is less than the atmospheric pressure beneath it, so it pushes it up. Also, if there's wind blowing over the top of your roof, it can have an upward force on the roof. It can blow your roof off. The reason for that, again, is that this moving air has a lower pressure than the stationary air below. Lastly, I want to talk about plasma. Plasma is the fourth state of matter after solid, liquids, and gases, and it is basically an electrified gas. So all the atoms or molecules in a normal gas are neutral, meaning there's the same number of electrons as protons in every atom. But in a plasma, the atoms that have been stripped of some or more of the electrons, and so the atoms themselves are positively charged, and they are coexisting with free electrons. And the sun, for example, is made of plasma. Also, fluorescent lamps that you see have plasma in them. So high voltage will cause electrons to travel through the gas, ionizing the atoms, and also providing a conducting path to complete the circuit inside the lamp. And that current will excite some of the mercury atoms and cause them to emit ultraviolet radiation, which interacts with some phosphor in the outside of the glass that's holding the lamp, and that causes the whole thing to glow in visible light. So this is also how plasma TVs work. So these TVs are composed of many, millions actually, of little pixels that are red, green, and blue, each containing a different gas. And these pixels are sandwiched between a whole network of little transparent electrodes. These electrodes are charged to produce electric currents, which generate light. It's ultraviolet light, which stimulates phosphors in the screen, and then which emit visible light that we see. And all these little pixels combine to make the image that we see on the television.